Good afternoon and welcome to this webinar, Boost ACR Energy Efficiency with Copper MicroGroove Tubes. This event, brought to you by the News and Appliance Design magazine, is sponsored by the International Copper Association and MicroGroove. I'm your moderator, Barb Checkett-Hanks. Thanks for joining us. Today's expert presenter is John Hipchen, President of Exel Consulting Group. John has over 14 years of experience with heat exchanger technologies, including the marketing of copper alloys and manufacturing technologies for brazing and soldering. Previously, he managed the development of new markets for specialized equipment systems. John graduated from Loyola University in Chicago and spent his early career working as a chemist. Before we begin the presentation, here are a few housekeeping items. To the left of the slide area, you will find a resource box. This allows you to click Help for technical difficulties, enlarge slides for better viewing, or download slides for a printable copy of today's presentation. You can even invite a friend to join us. If you need additional assistance, send an email to webinars@bnpmedia.com. Above the resource box, there is a blank questions box. Type a question into the box, then hit the Submit Question button to send it to us. Later in the live program, John will address as many questions as possible. Today's event is being recorded and archived on www.achrnews.com and on appliancedesign.com. All registered participants will receive an email within 1 to 2 business days that has a link to view a recording of this event. Now I'm excited to turn it over to today's presenter, John Hipchen.
Thank you, Barbara, and hello, everyone. My name is John Hipchen, and I'll be presenting this webinar today. On behalf of the International Copper Association and all its affiliates and copper centers around the world, I'd like to welcome everyone to this webinar. Today, we're going to review the technology behind MicroGroove tubes. We will understand why manufacturers can achieve higher heat transfer with less materials by using MicroGroove tubes. And we will compare the data from design studies that were performed by original equipment manufacturers, or OEMs. If you attended our first webinar on this subject, you will see a few familiar slides as we review the basics, but we have a lot of new data to share today, and that will take up the majority of our time. In the world of refrigeration and air conditioning, manufacturers are continuously challenged to reduce energy use, but competition forces them to do this in the most cost-efficient way possible. MicroGroove tubes are helping coil manufacturers and OEMs meet the demands of the market and at the same time maximize their cost savings and profit potential. Before we continue, I want to mention the MicroGroove.net website where the latest information about MicroGroove tubes can be found. At MicroGroove.net, you'll find news releases, technical papers, information about the suppliers of MicroGroove tubes, plus information about upcoming events and webinars. In fact, you can find links on the MicroGroove.net website that will take you to archived webinars that can be viewed on demand, including the webinar from last week and one from last December. And you might make a note that this webinar will also be available on demand. Today, we'll be talking about refrigeration and air conditioning coils that are made with round copper tubes and flat fins. And later in this presentation, we will take a close look at split-type units that have an outdoor condensing unit and indoor evaporator unit. Split-type systems can be found extensively in commercial refrigeration systems with oftentimes rather large condensing units such as this. The corresponding indoor commercial unit often looks like this, and anyone who has worked with walk-in coolers or freezers has probably seen this type of evaporator unit mounted near the ceiling. But all of us in North America are used to seeing the typical central air conditioning system that looks like this, with an A-coil evaporator that is mounted in the ventilation system and a U-shaped condenser unit that is mounted outdoors. In Europe and Asia, the split-type units look like this, and they often provide both cooling and heating. Another possibility with these split-type units are more than one evaporator unit indoors. And later in this presentation, we're going to look closely at data that was generated to optimize these exact systems. Round tube, flat fin coils have been used for a very long time, in fact, more than 100 years. But this photo, which is right out of an Internet heat exchanger catalog, this shows exactly the trend that we're going to discuss over the next hour. And that trend is towards smaller diameter copper tubes with special attention paid to the arrangement of the tubes. In this photo, the manufacturer advertises 35% more passes, and that's important because it translates to higher heat transfer, higher efficiency, less material is used to make the coil, and in many situations it also means less energy is used in the system. Note that in the new coil, the tubes are arranged in a staggered pattern, and we will see in this presentation how that can make a significant difference in the performance. So let's look at the advantages of MicroGroove tubes and the technology supporting this trend toward their use. The two main phenomena that contribute technically to the advantages of MicroGroove tubes are number one, reduced boundary layers, and number two, increased surface area. The name MicroGroove refers directly to both of these phenomena. Micro, referring to the small diameter tubes and the increased surface area that results from the small diameters, and groove refers to the internal enhancements inside the tube that reduce boundary layers. Together, both of these lead to dramatic increases in heat transfer. And improved heat transfer results in more energy efficient, smaller, and lighter coils, bringing about all of these benefits on our list of the manufacturers and distributors of air conditioning and refrigeration systems. Keep in mind that each of these benefits is not only associated with meeting energy and refrigerant regulations, but each benefit also means cost reductions or cost efficiencies that help all of us in an increasingly competitive market. Advantages like less refrigerant and less material are especially important to cost reduction programs. So let's turn now toward the technology behind MicroGroove tubes. Take a look at what happens inside a copper tube with respect to boundary layers. Whenever fluid moves through a tube, the fluid closest to the tube wall behaves differently than the fluid in the center of the tube. The fluid next to the tube wall sets up a boundary layer where heat transfer becomes more difficult. And this applies to the hydraulic motion of fluid, as well as the way heat moves from the center of the tube to the tube wall. So fluid closest to the tube wall tends to move slower than the fluid in the center. And even in turbulent flow, a laminar sublayer forms and heat moves slower through these boundary layers than it does in the faster moving fluid toward the center of the tube. Boundary layers act as an insulator and interfere with the heat transfer that we want. And here we see the boundary layer in a smooth tube. It develops and it does not dissipate or go away. MicroGroove tubes have internal enhancements to reduce the formation of boundary layers. These enhancements are grooves and proprietary patterns the tube manufacturers put on the inside tube wall. The exact configuration of the internal grooves and patterns is based on a long history of technical development and design, and is backed up by both experimental and field performance data. And the data clearly shows significant advantages with MicroGroove tubes. And this next slide shows why. In a tube with MicroGroove enhancements, you can see the boundary layer begins to develop, but it breaks down as it moves over the grooves. The additional mixing of the refrigerant that occurs inside the tube because of these grooves increases the amount of refrigerant that comes in contact with the tube wall. The positive effect on heat transfer from these internal enhancements has been known for a long time and applied commercially for over 20 years. And when combined with small diameter tubes, we have even more advantages that we're going to look closer at. When we compare tubes of different diameters, the first thing we might notice is that it will take several smaller diameter tubes to equal the surface area of a larger diameter tube. This is not a disadvantage. We actually have some important benefits here. A big one being an increase in the surface area to volume ratio, and that equates to more heat transfer. And with this increase in heat transfer, we don't need to match the volume or surface area of the larger tube to get the same amount of cooling. Another benefit is that in a smaller diameter tube, we can hold the same pressure as a larger diameter tube, but we can do it with thinner tube walls. And we'll soon see in case studies how important this can be to the overall cost of a system. So, when we reduce tube diameters, we can actually reduce the weight of the materials being used and in turn reduce costs. And as we continue to reduce tube diameters, we continue to gain surface area in relation to the amount of refrigerant that we have in the tube. And we can continue to reduce tube wall thicknesses while still meeting the same pressure criteria as the larger tubes. So looking at this from a different angle, we can handle higher pressures in smaller diameter tubes with the same tube wall thicknesses. The bottom line to all of this is that we can do a lot more with considerably less material when we use smaller diameter tubes. So once again, I want to emphasize that the reduction of boundary layers and increased surface area, they're the main technical factors that drive the benefits of MicroGroove tubes. Before we apply these advantages to the actual design and manufacture of coils, let's talk briefly about their impact on energy and our environment. Energy efficiency is typically rated one of three ways: the coefficient of performance, or the COP, the energy efficiency ratio, or EER, and the seasonally adjusted energy efficiency ratio, or SEER. When we look at how these ratings are calculated, we see that the COP does not have units because both the cooling load, Q, and the input power, W, are measured in watts, and watts cancel each other out. So for the purposes of this webinar, we'll look at EER ratings. Energy efficiency ratio is calculated by dividing the output cooling, measured in BTUs per hour, by the input electrical power in watts. So the units for energy efficiency ratio are BTUs per watt hour. The SEER rating is the same measurement, but it's adjusted to show energy consumption over a typical year of system cooling. EER, on the other hand, that covers a single cycle or even a specific point in the system's operation. Some manufacturers market individual products or even portions of their product line that meet the ENERGY STAR criteria. To qualify for the ENERGY STAR certification, products have to be about 10% more efficient than the minimum federal energy standard. And here we see the current Tier 2 ENERGY STAR specs that took effect on January 1st, 2009. Note the EER qualifications in the ENERGY STAR program. We'll be looking soon at performance data from various designs, and an EER of 12, that gives us a reference point to remember. There are a number of factors that a heat transfer engineer can look at when re-engineering refrigeration and air conditioning coils. The factors that we will focus on over the next few minutes are the tube diameter, the number of tubes, the total length of all the tubes in the coil, the number of tube rows in the coil, and the number of paths that the refrigerant can take as it passes through the coil. A change in any or all of these factors can affect these coil parameters and measurements. We call this set of criteria coil optimization, because the goal of an exercise such as this is to find a set of design factors that provides a more efficient, more compact, and less costly coil. A quote-unquote optimized coil design, if you will. The first three bullet points are all related. The amount of surface area is a direct result of the tube diameter, just as we discussed a few slides earlier. And the amount of surface area will have an effect on the heat transfer coefficient. The heat transfer coefficient, in turn, will drive the overall performance of the coil. The last two bullet points are important because the coil weight and refrigerant charge will have a big impact on the cost of the coil. So we will pay extra special attention to these numbers. We're about to look closely at design work. It was done by a research consortium in China, and it was done for two different OEMs. The Shanghai office of the International Copper Association has co-authored several papers with the Shanghai Jiaotong University's Institute of Refrigeration and Cryogenics. The studies we're about to look at were performed by this consortium in partnership with two different OEMs who will not be identified by name at their request, but rather we will refer to them as OEM number 1 and OEM number 2. In each of the case studies that we'll look at, the systems being studied are split-type, residential-sized air conditioning systems with outdoor condenser units and indoor evaporator units. Although these units are capable of providing both heating and cooling, you'll see they're very similar to the typical central air conditioning unit that's common in North America. And this data is absolutely relevant to those systems. In each study, several optimized designs were compared to an original design. We will compare in each case the original design to the optimized design that was found to provide the most benefits. A computer simulation program was used to project the performance of many of these design changes. And in order to make sure the simulated results were accurate, the research team first compared actual experimental data to the simulated data. and they determined that the heat transfer difference between the two was at worst only 0.2%. So this proved that the simulation software could accurately predict the performance of the various optimized designs. So let's take a look at the first case study with OEM number 1. And listed here are key parameters for the entire system for both the original design and the optimized design. We can see that R22 is a refrigerant, and the cooling capacity of this system is slightly under 2,600 watts for both designs. Note that the optimized design has roughly the same cooling capacity as the original. Since we're interested in EER values, if we convert the watts to BTUs and then divide by the input power, we get our EER number, and we can see that we're working with a system that just meets the current Energy Star criteria of a minimum 12 energy efficiency ratio. And looking at the entire system, a very important factor to an OEM is the weight of the tubes and fins used in both the evaporator and condenser coils, because these weights are directly related to cost. And when we do compare the weight of the tubes and fins, original design versus optimized design, we see weight reductions for the optimized design in both the copper tube weight and the aluminum fin weight. So we know the optimized design will be less expensive to produce than the original. And keep in mind that the optimized design is doing the same amount of work. So let's look closer now at each of the coils used in this system. In the cooling mode of operation, this is the indoor coil, and it's acting as the evaporator. Let's first compare the factors that we know translate most easily to material costs. And those factors are the weight of the tubes and fins. Looking at the total length of tubes in each design, we see that we have the exact same total tube length for the original design as we have for the optimized design. If we add up the lengths of each tube in the coil, that is the number we're talking about here when we refer to total tube length. Although those numbers are the same for each design, the optimized design uses smaller diameter tubes, 5 millimeter versus 7 millimeter. And we see a considerably smaller tube wall in the 5 millimeter tube than the 7 millimeter. The result here is 420 grams less copper in the optimized coil. And a quick look at the fin pitch tells us with the tighter spacing of the smaller diameter tubes, we have a denser coil with slightly more aluminum in the optimized design. Because the tube diameter was reduced in the optimized design, but not the total tube length, one might expect the pressure drop in the optimized coil to be higher. But note the number of rows and refrigerant paths. We see that the optimized coil has 4 refrigerant paths versus only 2 for the original design. A quick look at the indoor unit tells us that this coil is long and somewhat narrow. We will be looking at several circuit diagrams like this. And these are illustrations that we think are a little easier to understand at a quick glance than what we typically see for circuit diagrams. So keep in mind when we're looking at these that they're not actual coil images, but just representations of the refrigerant path through these coils. And here we see the circuit diagram for the original design that has the 7 millimeter tubes. and it shows the two refrigerant paths. It's fairly straightforward. Here is a circuit diagram for the indoor coil with the optimized design showing the 4 refrigerant paths. This is much less restrictive path for the refrigerant, and it will result in a lower, more acceptable refrigerant pressure drop across this indoor coil. So now let's look at the outdoor coil. We're going to look at this just as we did with the indoor evaporating unit, and we'll compare the original design of the outdoor condensing coil with the optimized design. We have the same difference in tube wall thickness between the 9.52 millimeter or 3/8 inch tubes and the 5 millimeter tubes. But we see a more than 50% increase in the total tube length of the optimized 5 millimeter design. However, because 5 millimeter tubes weigh less than half of a 9.5 millimeter tube, we see a reduction in the tube weight of 435 grams per coil. And in the outdoor unit, the weight of the aluminum fins has dropped by almost a kilogram per coil. So now let's look at the rows of tubes and refrigerant paths. The heat transfer engineers did something a little different with the optimized design of this outdoor unit. They added another row of tubes, but in this extra row, the tubes are only half the length of the others, and we go from just 2 refrigerant paths to 5. And here is what they did. The original design moves air horizontally through a curved coil made of 2 rows of 9.52 millimeter copper tubes. The illustration here is just showing us the concept. This is the circuit diagram showing the paths that the refrigerant travels through this coil. Notice that the refrigerant flows the opposite direction of the air. We've got the inlet on the right, the outlet on the left, but air moving left to right. This slide depicts the optimized coil for the outdoor unit. And you can now see what they meant by a half-length row of tubes. This design, it maintains the original concept, but it uses considerably smaller diameter tubes than the original design. And again, when we look at the 5 paths that the refrigerant can take in the optimized design, and we compare it to the 2 paths in the original, we can understand how the pressure drop is managed with the much smaller 5 millimeter tubes. The multiple paths offer much less tubing to flow through, and therefore a minimal amount of pressure is lost in the process. And be sure to note the nearly identical pressure drop measured in the original versus the optimized coil. Also, the inlet and outlet now show the refrigerant flowing the same direction as the air. Summarizing this work with OEM number 1, now that we have looked so closely at the details, let's look again at those parameters for the entire system. The optimized design offers equal to possibly better cooling with equal input power. There is no sacrifice to the energy efficiency rating. There is no sacrifice to pressure drop. And all of this is done with significantly less material. It's going to make an accountant somewhere quite happy. So let's look at another study. Let's look at OEM number 2. And that's what we've got now. And we're looking at a completely different system here. But we're looking for the same type of competitive edge with this optimized design. So we will run through this data just as we did for OEM number 1. Compared to OEM number 1, we have a slightly lower cooling capacity. but considerably more input power. So we see a lower EER of 10 compared to the EER of 12 that we had with OEM number 1. So this system would not qualify for the Energy Star certification. The optimized design in this system provides almost a kilogram of weight savings per unit on the copper tubing, but we see a slight increase in the weight of the aluminum fin. And in real life, this manufacturer found the cost savings from the smaller diameter MicroGroove copper tubes to be significant enough to justify proceeding with this design in production. Notice here that the optimized evaporator coil goes from 7mm tubes down to 5mm, but does so with more total tube length. But once again, due to the lower weight of the 5mm tubes, there's a weight savings of 262 grams per coil. A smaller fin pitch means a denser coil, but the weight savings in aluminum fin material, that indicates we've probably got a more compact coil. Our optimized design in this case only has one more refrigerant tap than the original and maintains the same number of tube rows. Here's the tube circuit diagram for the original design of the indoor coil for OEM number 2. And we can see an already fairly unrestricted design with 2 paths. Note the inlet on the left and outlet on the right. It gives us refrigerant flow in the same direction as air. Looking at the optimized design here, we see 3 distinct refrigerant paths, again allowing an acceptable pressure drop with the smaller diameter 5mm tubes. Note the inlet and outlet are now reversed from the original design, resulting in refrigerant flow in the opposite direction of the air. Now let's take a quick look at the outdoor coil parameters and remember the type of factors that we're looking for here. We see some familiar themes. We have lower tube wall thickness in the 5mm tubes versus the 7mm, more total tube length with the 5mm tube design, but again, significantly lower weight. The weight of the fins is almost the same, with a slight increase for the optimized design. Looking at the number of tube rows and refrigerant paths, we see the same number of rows, but interestingly, a reduction in the number of refrigerant paths. We're going from 5 in the original to 4 in the optimized design. So let's see what's going on here. When we look at the original design circuit diagram, we see some T's and some sharp 90-degree turns in the refrigerant path. And when fluid makes a sharp, sudden change in direction, like we see happening in this circuit diagram, it can cause a considerable pressure loss and be restrictive to the flow of refrigerant. In the optimized design, T's and sharp turns are minimized. This less restrictive routing could be one reason why we see fewer refrigerant paths in the optimized design, even though we are now using smaller diameter tubes. Note that the pressure drop for the original versus the optimized design, both of those numbers are nearly the same. And looking one more time at the key system parameters for this design study, once again we see equal performance with less material. In the 2 studies that we've just gone through, these OEMs did not report the refrigerant charge, And that's an important factor in the cost of a refrigeration or air conditioning system. So let's take a look at refrigerant charge data that was collected over the last year. This time, the OEMs that contributed the data approved the release of their names. So we see in this chart 3 different manufacturers. We see 2 different types of systems, window units and split type systems, and 3 different refrigerants. If you don't recognize R290, that's the name for propane. When we compare original to optimized designs, we see that the window unit goes from 7mm to 5mm tubes for both the evaporator and the condenser, while the split type systems, both of them, reduce from 7mm to 5mm tubes for the condenser coils only. And, as you might expect, it is the window unit that reports the largest percentage reduction of refrigerant charge. But even the smallest refrigerant charge reduction, shown here of 20%, that's still quite sizable, and I'm sure welcome news to the accountant that's watching the bottom line. All of the comparisons we've looked at so far have been between different diameters of round copper tubes. So now let's look briefly at a comparison that includes aluminum microchannel tubes. This Italian company, Luva, they optimized an existing condenser with conventional 9.52mm tubes, and they reported their findings last year at a conference in Stockholm, Sweden. Although this is yet another completely different study, at this point you can probably pick out the important factors here rather quickly now. The column that's labeled SHVN 19/0, that represents their original design, and we see that the 2 optimized designs match the cooling capacity rather nicely, all right around 20 kilowatts. Their existing coil had 9.52mm tubes, and in the trial designs, they used aluminum multi-channel tubes and 5mm copper MicroGroove tubes. And in this row, you can see that they were able to reduce the refrigerant charge in the aluminum tube design to about 51% of the refrigerant used in the existing design. But the 5mm copper tube design only used about 44% of the refrigerant compared to the original design. And that's a further reduction of refrigerant charge by another 16 or 17%. If we look at the size of the header required in the aluminum design, we see a diameter of 38 millimeters, and that, the company reported, was the minimum diameter that they could use to ensure proper tube-to-header joints and refrigerant flow. A header that size requires a considerable amount of refrigerant to fill that space. And this explains that extra 16% refrigerant reduction that we see with the 5mm tubes compared to the aluminum microchannel. Before we turn our attention toward manufacturing practices, let's summarize the coil design issues we talked about relative to smaller diameter MicroGroove copper tubes. Small diameter MicroGroove tubes allow for energy efficient designs. They allow manufacturers to use less materials and less refrigerant, and the coils they produce are proven, durable products with a history of success behind them. Small diameter MicroGroove tubes allow engineers the flexibility to design for a wide variety of operating conditions, and this is a manufacturing process that's proven, it's economical, it's robust, and it's familiar to the entire industry. And finally, this process is supported by a supply chain that's very well established with manufacturing and distribution centers worldwide. So let me say a few words now about manufacturing practices. We all know that coils are made from tubes and fins, and we know that the tubes are inserted into the fins and then expanded to mechanically fasten the tubes to the fin. Tube expansion also ensures good contact between the tube and fin, and that's critical for the heat transfer that we need. As smaller diameter tubes are expanded, axial tube shrinkage can become a problem, and the International Copper Association's team in China supported the development of cost-effective tube expansion technology that controls tube shrinkage and maintains tension on the expansion tools for high manufacturing yields and long tool life. This technology basically secures the tube end during expansion in order to prevent shrinkage. So this method of manufacturing coils continues to set the industry standard for corrosion resistance and reliable service life. Since this process remains largely unchanged for small diameter microgroove tubes, engineers and technicians throughout the industry are familiar with the practices and also the costs associated with it. And in conclusion, I want to remind everyone once again to visit the microgroove.net website where you can get additional information, and you can also leave questions, and we will respond to questions that come in through this website. I want to thank you for your attention. At this point, I'd like to turn the program back to our moderator, Barbara, for the question and answer segment. Thank you very much.
Thank you, John, for a great presentation. Now we'll address some of the questions that have been submitted throughout the program. First, which manufacturers are using MicroGroove?
There are a variety of manufacturers in China. All of the manufacturers that we showed in the chart, you might recall, are using them. That would include Medea and Kalon, and as well, I think Haier was in there.
Right.
And anybody can contact us for more information in that regard.
Okay. One attendee would like to know, how can we manage the extra pressure drop from small tubes?
Well, the extra pressure drop from small tubes, as you saw in the case studies that we showed, is best managed by redesigning the refrigerant pass. And more pass, multiple pass, help manage that refrigerant pressure loss that is typically higher with smaller diameter tubes. But as we showed several times, that pressure can easily be managed to match the pressure of the current design system.
Okay. Someone else would like to know, is there an aluminum microgroove?
I believe there is, but I don't think it goes down in as small diameter as the copper microgroove tubes do. And aluminum being a softer material, the internal grooves are susceptible to deformation during that expansion process, during the manufacturing process. And that's something that a manufacturer has to watch if they're using aluminum internally enhanced tubes.
Now, you mentioned propane. Has this been used with carbon dioxide, CO2 systems?
This copper microgroove tubes are, in fact, being looked at for CO2 designs, and I believe there are OEMs that have generated data on those systems. If somebody is interested in that, I would suggest they get a hold hold of us separately, and we'll see what kind of data we can dig up. Most of those studies, though, are tend to be proprietary at this point. But like I said, we can see what we can dig up that we'd be able to relay to the outside world.
Okay. One attendee would like to know, will the closer tubes and condensed aluminum fin pattern cause higher static pressure drops with regards to airflow?
That could be a concern. It was, I'm sure it was measured in this study. I don't have the exact air pressure drops in front of me, but again, you would balance that in the design of the coil. That's really a fin design issue, and again, that would be an issue that would be more details on that would best be discussed outside of this webinar.
Okay. Is MicroGroove a patented idea?
The name MicroGroove is trademarked, and different various companies do have patents on the patterns and the specific design of the grooves on the inside of the tubes. Those patents would be held by the manufacturers of the tubes. So that would be the extent of patents relating to the tubes themselves. There are numerous patents on different designs of heat exchangers that appear to be novel and different from existing technology. So there are patents out there. Somebody who thinks they have a new idea would need to do a patent search. But the name MicroGroove is trademarked, and the patents only relate that I know of to the tubes themselves. And again, like I said, any heat exchanger design, you would have to do a patent search on.
Okay. One person would like to know, what about the oil? What is the effect of the grooves?
The effect of oil in a refrigerant, it definitely does reduce slightly the amount of heat transfer that you can get, and we have studied data that demonstrates that. But you still have a much higher heat transfer with a MicroGroove tube than you would compared to a smooth wall tube, regardless of whether there's oil in the refrigerant or not.
Are there any products out there that use MicroGroove tubes which have not affected the performance and were able to achieve the cost reduction?
Yes, there are, and I believe here in North America, Goodman, in fact, markets a coil they call a smart coil, and that's a pretty good example of how they've done exactly what we're talking about here, and achieve that with a cost reduction.
Is MicroGroove the same as inner grooved tubing design?
It is. As far as referring to the internal patterns that enhance heat transfer in a round copper tube. MicroGroove, though, the way it's being used by the International Copper Association, refers to more to the smaller diameter internally enhanced copper tubes.
Is this technology applicable for 3/8-inch tube only?
No. As you saw in the case studies, several of those reduced from a 7 millimeter to a 5 millimeter and achieved significant benefits. And we don't really know the limit yet to the minimum diameter that we can go. I'm sure there are limitations manufacturing-wise, but nobody's really established yet just how small a diameter we can go to.
Okay. What is the difference between microgrooves and spiral inserts?
Well, spiral inserts is, from the way I understand it, that's a separate piece. So it's almost a second piece that's inserted inside of a round tube. MicroGroove tubes have that internal enhancement put into the internal wall. There aren't two pieces in a MicroGroove tube. It's a single piece, and like I say, the internal crosshatch patterns and however proprietary design they use to get the internal enhancement, that's either rolled into the surface of the internal tube wall during manufacture, or it's put in there if it's an extruded process. That's done during the extrusion. Like I say, again, the difference between those two would be you have a two-piece type of system with an insert. It's a one piece with a MicroGroove tube.
Okay. Is there a pressure threshold concern with the smaller diameter tube walls?
Well, I'm sure, eventually, if you continue to increase the pressure in a round tube or any tube, it will eventually burst. So there is a pressure threshold, but you can achieve much higher pressures with a smaller diameter tube than you can with a larger diameter tube when you're looking at the tube wall thickness. So as you saw in the case studies, I believe we had a tube wall thickness of about 0.28 millimeters in the 9.52 millimeter tubes and the 7 millimeter tubes. That tube wall thickness was reduced to 0.2 millimeters, which is considerable drop in wall thickness and leads to a considerable drop in materials from a weight standpoint. So depending on how high the pressure is, you will be able to handle much higher pressures in smaller diameter tubes with smaller tube wall thicknesses. Bottom line is, like I said earlier, you'll be able to do a lot more with a lot less material in a smaller diameter tube.
Does MicroGroove create an improvement for all Freon refrigerants?
The quick answer to that is yes. I do not recall a study with any particular refrigerant that did not show some sort of enhanced heat transfer with the MicroGroove tube. And again, the reason for that is because of the boundary layers that are reduced with the MicroGroove tube. Doesn't matter what refrigerant you've got or what media you're using, when you reduce those boundary layers, you're going to get better heat transfer.
Now, this is a related question. Does the refrigerant type alter the MicroGroove design, or is it standard for all types of refrigerants?
The MicroGroove design is fairly standard for all refrigerants, but as you would expect, the heat transfer and pressures are going to vary as you go from one refrigerant to another. But you don't see too much change in the type of enhancements in the MicroGroove tubes. Like I mentioned, you're still going to get a superior heat transfer with the MicroGroove tube.
Is the cost of the microtube comparable with smooth tube on a weight basis?
Well, the price of a tube is going to be divided into, of course, the cost of the metal and the cost of fabrication. And it's going to cost more to fabricate a MicroGroove tube. But when the overall weight is so much less, our studies that we've looked at have shown considerable cost savings, as we indicated in the data that we demonstrated. So the weight savings just in the metal cost is usually going to far outweigh the increase that you might have with in fabrication for the enhanced tube.
Can MicroGroove tubes compete on a cost level with multi-port extrusion aluminum tubes?
We believe they can, and that's what we've tried to demonstrate today. And we also believe that they offer a lot more design flexibility to the engineer who's designing coils. With a micro channel tube, that's a flat tube, regardless of whether it's made out of copper or aluminum. There's only one path that air can travel going through that coil. The round copper tubes allow an engineer to allow various options on how those copper tubes are distributed, and as air flows through that coil, you can break down boundary layers with the placement of the copper tubes. Air acts just like any liquid fluid regarding the boundary layers that I talked about earlier. So we do see that these are competitive on a cost basis, and we also think that they're going to have a place in harder to deal with conditions, if you will. So yes, we definitely see them as being cost competitive.
How does this design compare to multi-flow automotive condensers? Is it better or not?
Multi-flow automotive condensers, that's a question that I would suggest they send to us offline, and we'll get back to them with an answer on that. I'm not as familiar with multi-flow automotive condensers.
What is the status of the development of air conditioners with smaller diameter copper tubes among the OEMs?
It is being used quite heavily in China, and as we mentioned, a lot of this work was done in China, where a considerable amount of air conditioners are manufactured. So the status is that this trend is seen quite readily in China. It's starting to be seen in North America as well. The typical 3/8" 9.52 millimeter tube is still quite common in North America, but we are starting to see manufacturers switch to smaller diameter tubes for exactly the reasons that we presented today.
Okay, we have time for one last question here. Are you saying that the standard 3/8" refrigeration tube will disappear soon?
No, not at all. In fact, I am sure that it will remain quite common. There's certainly a place for that tube, but what I am saying is that there are a lot of benefits to switching to smaller diameter MicroGroove tubes, as we explained today, and we are starting to see that trend take hold in North America. It's, as I mentioned, it's already taken hold quite a bit in China and Europe.
Okay, I'm going to slip in one last question here.
All right.
Are MicroGroove tubes suitable for tin plating?
To my knowledge, they are, and I would imagine you would do that for particularly corrosive environments, and I believe they are, and we could look into that further and put somebody in contact with companies that would do that.
Okay, looks like that will wrap us up for now. This concludes today's webinar. Please join me in thanking our excellent presenter, John Hipchen, as well as our sponsors, the International Copper Association and MicroGroove. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments to help us serve you better. If you have any additional questions or comments, please don't hesitate to contact me at checkitb@bnpmedia.com. We appreciate your time and hope you have found this webinar to be a valuable experience. Thank you.